This is Jane. Jane is the logistics manager of Walmart. For a few years now, customers have been going crazy for vegan meat, especially chicken nuggets from Impossible Foods. Impossibles Incorporated has its factory in San Francisco, which is quite a distance from Walmart stores on the East Coast. So Jane wonders which is cheaper, to have the products shipped directly from Impossible Foods to the stores or to the distribution centers. Luckily, Jane had taken the operations management course at the University of St. Gallen and therefore knows that this problem can be solved with the help of linear programming. Linear programming is used to find the optimal solution to a problem where constraints apply. Linear programming is used, for example, in marketing to distribute the marketing budget across different media channels. In production companies, it is used to allocate the optimal allocation of resources such as material, machines, or manpower between the different departments. Or even companies like Amazon or FedEx use linear programming to find the shortest and most efficient delivery routes. But how is linear programming actually applied? Let us look into how linear programming can be solved graphically.
In a simpler example, problems such as these can be solved using a two-dimensional optimal solution space graph with two variables. We first set up an objective function and constraints, which we then plot. In order to plot a constraint, we replace the inequality sign with an equal sign, making it a linear equation. We then determine their intersects, for which we set the x variable equal to 0 and solve. We then plot this line. This gives us the feasible region. The shading below the line corresponds to the less than or equal to sign. The feasible solution space results from the plotting of all constraints and shading their overlapping region. Next, we plot the objective function. For that, we set it equal to some amount and solve to yield integer values. Then move the parallel line until the feasible region is fully integrated and identify our optimal point. This will tell us which constraints intersect there. Through solving of simultaneous equations, we obtain the optimal decision values. Lastly, we substitute these values into the objective function and solve. Let's now see why a more complex problem such as ours requires a different approach. In our example, Impossible Foods has 12.5 million packages of frozen chicken nuggets, which must be shipped from their headquarters in San Jose to various locations across the U.S. It has the choice to either ship to the distribution centers of Walmart in Jersey City or Dallas, or ship directly to their stores located in 5 distinct states. As we will find out later, Impossible Foods may either face cost advantages or disadvantages through their collaborative distribution routes with Walmart. The demand of each Walmart store consists of the following, all adding up to 12.5 million chicken nuggets. These values will later be incorporated into our constraints. Another essential element are our decision variables. Decision variables represent choices available to the decision maker in terms of amounts of either inputs or outputs. For example, some problems require choosing a combination of inputs to minimize total costs, such as the choice facing Impossible Foods. Another linear programming assumption is relevant here, namely certainty. This claims that the values of parameters are known and constant. The decision variables which support this linear programming problem are the following, each matching a potential route with its price. Another important linear programming assumption is at play here, namely proportionality. Proportionality claims to produce logical results based on the fact that if 1 unit of a product costs $1, then a greater number of that product will create costs of equal proportion. This leads us to our objective function. The objective function is a mathematical expression that can be used to determine the total costs for a given solution. Thus, an optimal solution to the problem is the solution that achieves the best value for the objective function, in our case, a minimization of the costs. One of the essential properties of linear programming fulfilled with our objective function is linearity. This requires that the impact of decision variables is linear in constraints and the objective function. Another important assumption is divisibility, allowing non-integral values of decision variables. Essential to all linear programming models, there must be a set of logical constraints, restricting the alternatives available to the decision maker. The 3 types of constraints relate to greater than or equal to, smaller than or equal to, or equal to. A linear programming model can consist of 1 or more constraints defining the feasible combinations of decision variables, also called the feasible solution space. Combining our required demand with the route denominations, we achieve our first constraint. Each constraint is composed of the potential routes leading to the respective store as a final destination, adding to their total demands. There must also be a balance in the distribution centers, allowing them to transport all required amounts to their final destinations. In our example, the intermediaries cannot accumulate inventory at the end of the foreseen distribution period. What they receive is now equal to what each has to transport to the stores. Coming to our third constraint, regarding the processing capacity in the distribution facilities. These constraints show that the distribution centers cannot receive more chicken nugget packs than they can process. Coming to our fourth and last constraint, a political restriction on monopoly laws has reduced the capacity of the route between Impossible Foods and New York to quantities of 1.5 million, leading to the following constraint. In a final step, we respect the linear programming assumption of non-negativity, where negative values of decision variables are unacceptable and are thus removed from the possible solution space through the following constraint. Now, let's apply linear programming. Firstly, we list all our possible routes according to the names we've given them, along with their corresponding unit costs. The row above will remain empty, as it will be the responsibility of the solver to place its determined decision variables there according to most advantageous cost and quantity. Now we define the target function. The target function is defined as the sum product of the decision variables, which will be the chosen quantities, multiplied with their respective costs and then added together. We then use the table below to insert our linear demand fulfillment constraints. Each one represents a route we must respect and consider in our total demand. Coming together, the demand constraints are listed on the right-hand side, which must be fulfilled by the solver calculation on the left-hand side. The below constraints of capacity balance, processing, and route capacity, which are considered with a similar setup through the use of ones in each field, which must be considered in the constraint and result in a similar left-hand side/right-hand side equation taken from our given constraints. Now that we have finished the basic setup, we can let the Excel solver finish the task. Within the solver, we now define the objective cell, which contains the objective function of our total cost function. The goal will be the minimization of that function / the costs, which also must be specified by the following. Furthermore, we're giving Excel the permission to change the decision variables within the decision variables row, also shown by the following. We also set all constraints which are defined above into the Excel solver through the following. In a final step, we make sure the simplex mode is being applied and the non-negativity of values is identified. The simplest step is now to let the solver solve the problem. Included in this, we can choose to generate an additional element being the sensitivity report, which will be explained later. As we can see, the solver has identified the lowest possible cost for our target function and given its corresponding quantities shipped through each route. The cheapest routes are the ones which are direct and not being transferred through the Walmart distribution centers, simplifying the shipping process and cost problem for Impossible Foods. The sensitivity report details how changes in our coefficients of the objective function and in the right-hand side demands affect the solution. As portrayed here, there exist two aspects, one of which are the variable cells and the second being the constraints chosen. The sensitivity report on the variable cells shows the ranges of optimality, creating a range of variables which the objective coefficients can take on without changing the optimal solution. In our Excel sheet, we have calculated these upper and lower limits for the coefficients. Here we show the allowable increase or decrease, as well as how we got to the solution. The reduced costs shows by how much the profit, or in our case the costs, will increase if we add 1 unit of a respective decision variable. Another aspect are the ranges of feasibility, which represent a range for the right-hand side of the constraints which leave the shadow price unchanged. The shadow price represents the marginal change of the objective function if a right-hand side constraint is changed. Here, we also calculated the upper and lower limit. In a final step, to highlight, values of distribution center 1 and processing capacity 1 are slack variables, since their final values are less than on the right-hand side of the constraint. The others are defined as binding constraints. Although linear programming sounds like a simple way to solve optimization problems, it has certain limitations. On the one hand, it is not easy to define a specific objective function, and even if a specific objective function is laid down, it may be challenging to find out various technological, financial, and other constraints which may be operative in pursuing the given objective. On the one hand, the assumptions of linear programming are unrealistic. It assumes that factory proportion remains constant and that the values of coefficient of decision variables are known with certainty. Due to this restrictive assumption, linear programming cannot be applied to a wide variety of problems where values of the coefficients are probabilistic. Furthermore, the input-output, production cost, and production total revenue relationships are considered to be linear. All these assumptions imply constant returns to scale and perfect competition in the market. But in fact, the relations are not always linear and imperfect competition prevails in the market. Finally, decision variables in linear programming can accept non-negative integer as well as fractional values. However, we frequently encounter scenarios in which planning models include integer-valued variables. Trucks in a fleet, generators at a power plant, pieces of equipment, and investments are only a few examples. Rounding off the solution to the nearest integer will not yield an optimal solution. In such cases, linear programming techniques cannot be used.